So this is the lecture on the method of reductions of order. Given if we have a second order in this form, y double prime plus bt y prime plus ct y equals 0, then, and given that we know a solution to these equations, we can actually try to find the second solutions of these equations, which in the form of the products of the first solution multiplied to an arbitrary function v. And let's see if we can find function v, we can multiply v to y1 to get the second solution y2. So in order to do this, to use this method of reduction of order, keep in mind that you need first, your equation needs to be in this form, in the form of y double prime. The coefficient of y double prime has to be 1, and the coefficients of y prime should be a function in term of t, and the coefficient of y should be a function in term of t as well. And another condition to use in order to use this method is you should know one solutions to these equations, and then your goal is you want to find the second solution via this arbitrary functions v. Once we find v, then we can find the second solution. Now, how can we use this method? First, we want to do a substitutions here. Let u equals v prime. So then we know that u double prime equals we know that u prime equals v double prime. And let's now consider the differential equations y1 u double prime plus 2y1 prime plus bt y1, everything multiplied to w equals 0. How did we get to these equations? I remember in class that we went through the process of how we got to these equations by plugging in the solution y2 into the differential equation and do some manipulations with the fact that y1 is a solution to the differential equation. We concluded that this equation here is the equation in terms of w and y1 prime that we get. Alright, now we can solve for w. You can use either separable equation or integrating factors, whichever method that you are more comfortable to use. Then once you solve for w, then you can integrate w in terms of t to get v. And once you get v, an easy step is to multiply v to y1 to get y2. Okay. Now, and once you have y1 and y2, you should check if y1 and y2 forms a fundamental set of solutions using Gronsky determinant. Let's look at an example. Let's try to we want to find the general solution for this equations 2t squared y double prime plus 3t y prime minus y equals 0, given that one of the solution is y1 equals 1 over t, with condition that t is positive. Now, following the process, we let y2 equals y1 times v, and we let w equals v prime. And then we can consider an indeterminate, but then the next step is we have to determine b of t, which is the coefficient of y prime. And in this original equation, you can see it here, the coefficient of y double prime is not 1. So we have to make it equals 1 by divide everything by 2t squared. And once we divide everything by 2t squared, we can determine b of t is 3 over 2t. Now, once we have b of t in the right form, we can consider the equations y1 w prime plus 2y1 prime plus bt y1 times w. We can replace that y1 is 1 over t, y1 prime is negative 1 over t squared, bt is 3 over 2t, and y1 is 1 over t. Okay. Then the next step is you want to solve for w. separable equations here, and you can get to this equation. You separate it to two sides, integrate both sides to get W. The result for W is W equals C1t to 1/2. And once you have W, you can solve for V by integrate W in terms of t. And then the result for V should be 2/3 C1 t to the 3/2 plus C2. Once you have V, then the next step is you want to multiply V to Y1 to get Y2. And this is your Y2 at first. Y2 equals 2/3 C1 t to 1/2 plus C2 times 1/t, but you can see that C2 times 1/t is the same as Y1. So we should ignore this function because it's repeated the same solution Y1. And then the only left is 2/3 C1 t to 1/2, which we can ignore this constants here, and we're just trying to extract the function y2, which is t to 1/2. At this point, you ignore the same solution set, the same solution to y1, and you also ignore the constants. You just need to extract the function itself. So then at the end, the determinant at the end, y2 should be t to 1/2. And then the last step is you need to check if y1 and y2 forms a fundamental set of solutions by using Kronskian determinants. And I use Kronskian determinants. I have a setup like a matrix 2 by 2 matrix. So this is my y1, this is y2, this is y1 prime, this is y2 prime. And the Kronskian determinants is the determinants of this 2 by 2 matrix. So I would take y1 times y2 prime minus y1 prime times y2. And the result is 3/2 t to the negative 3/2. And you know that this is exponential function when t is positive, so this numbers is always positive, is always non-zero. Since it's always non-zero, we can conclude that y1 and y2 here is a fundamental set of solutions.